At first glance, Chongqing East looks like an enormous train station, but the real engineering is hidden in the levels beneath the tracks. Across this site, the ground changes elevation by roughly 30 to 50 meters. Instead of forcing every part of the project onto one common level, engineers used that difference in height to build the transport hub vertically, stacking railway infrastructure, passenger spaces, roads, and urban transit connections inside one enormous system. Then came the roof. One steel roof section alone weighed about 4,400 metric tons. Instead of trying to place the entire structure with conventional cranes, engineers raised it as one synchronized system. And elsewhere in the complex, another giant roof faced the opposite problem. It did not need to move up, it needed to move sideways. So how did engineers turn difficult mountain city terrain into one of China's most extraordinary railway hubs? This is Chongqing East, and this is how it was built. To understand the station, start with the ground. Chongqing is a city shaped by steep hills, valleys, and dramatic changes in elevation. Roads climb slopes, bridges cross low ground, railways disappear into tunnels. In some parts of the city, two streets separated vertically by several floors can both appear to be at ground level. That geography is part of Chongqing's identity. For engineers, it is also a constraint. Chongqing East was developed in the Chaiyuan area of Nannan District beside the mountainous terrain around Qiaoping Mountain. Across the project area, the difference in elevation is roughly 30 to 50 meters, about 100 to 165 feet. For a major railway hub, that matters. Railway platforms need controlled levels. Train movements need predictable geometry. Roads, public transportation, and passenger circulation all have to connect with the tracks. And large stations normally consume enormous amounts of horizontal space. One conventional response would have been to spend much more of the site forcing railway and transport functions toward a common elevation. Instead, the designers exploited the height difference. Different systems could occupy different levels. The terrain would not simply surround the station. It would help determine its form. But before the hub itself could work, millions of passengers and vehicles still needed ways to reach it. The road network around Chongqing East became a major engineering project of its own. By 2024, the supporting backbone roadworks around the hub had involved roughly 9.72 million cubic meters of earthwork. That number does not describe excavation for the station foundation. It belongs to the wider road infrastructure required to connect the project through difficult terrain. Those supporting works included 6 bridges and 5 tunnels. That combination explains the geography better than a flat road plan ever could. The approaches repeatedly had to move over the landscape or through it. A giant station cannot operate as an isolated building. Every train arriving with hundreds of passengers creates demand somewhere else, at roads, transfer areas, metro connections, drop-off zones, and public transport interfaces. So engineers were solving the terrain outside the station at the same time they were solving the structure inside it, and the most unusual decision was still ahead. The core station and hub zone measures roughly 620 meters by 650 meters. At that scale, the project begins to behave less like one building and more like a piece of city. The entire integrated railway and transport hub covers roughly 1.22 million square meters, around 13 million square feet. But that number needs an important distinction. The 1.22 million square meter figure describes the entire integrated station and transport hub. It does not describe one enormous passenger waiting hall. The railway station building and railway-related works represent a much smaller part of that total, roughly 120,000 square meters. The larger complex works because many of its functions are stacked vertically. The integrated hub was organized across 8 levels. The passenger station itself operates across 4 main floors. Those are not contradictory numbers. 8 levels describe the larger transport machine. 4 main floors describe the passenger station itself. Inside the overall complex, railway infrastructure, passenger circulation, road systems, urban transit connections, and supporting functions occupy different elevations. In a flat city, engineers often separate these systems by distance. Here, they could also separate them by height. A road could arrive at one elevation, passengers could transfer through another, railway tracks could cross above occupied space, urban rail could connect below. That was the real meaning of building vertically. But there was one enormous obstacle: the railway itself. A conventional railway yard often sits on a ground-supported formation or embankment. That is efficient for trains. But an embankment also occupies the entire volume underneath the tracks. At Chongqing East, losing that volume would waste an extraordinary amount of space. So engineers changed the relationship between the railway and the building. Instead of letting the railway sit on a massive solid embankment through the hub, the project adopted what official material describes as bridge building integration. The simplest way to understand it is this: the bridge is inside the building. The railway was carried on an elevated structural system integrated with the hub below. Trains could still move across the top, but underneath, the space remained usable. That decision opened roughly 556,000 square meters, nearly 6 million square feet, of building space beneath the railway. Space that a conventional embankment would otherwise have occupied. Official project material also says the solution saved roughly 200,000 square meters of land compared with the embankment alternative. For a station constrained by mountainous urban terrain, that is a major advantage. But the space came with a structural price. Once the railway sits above occupied parts of the building, engineers can no longer design the railway and the building independently. Railway supports affect usable space below. Building geometry affects where those supports can go. Passenger circulation has to move through the same structural grid. Road and transfer levels interact with both. The railway needs a continuous, stable load path. The building needs large spaces for people and vehicles. Both have to coexist in the same volume. A land use solution had become a structural problem, and as the concrete and steel frame rose, the scale of that problem became obvious. The early construction stages still involved familiar elements of a major building project: excavation, reinforced concrete, columns, beams, and increasingly large structural bays. But Chongqing East needed unusually large open spaces. Passengers had to circulate through vast halls. Platforms had to remain open along long railway alignments, and the roof had to cover enormous areas without filling the station with closely spaced columns. Official project material puts the station's structural steel quantity at roughly 45,000 metric tons. Some of the roof spans reached approximately 72 meters. That is about 236 feet. At that scale, the roof stops behaving like a simple cover. It becomes a mega structure of its own. And that creates a construction problem. The final roof may be tens of meters above the floor. But assembling thousands of tons of interconnected steel at that height is difficult. Workers need access. Connections need precision. Temporary supports become larger. Cranes need more reach, and wind becomes more important. For one enormous section, the project team chose a very different method. They built the roof lower down. Then they lifted the entire structure. The roof section covered a projected area of roughly 54,000 square meters. Its weight was about 4,400 metric tons. The problem was not simply lifting that much weight, it was lifting one huge connected steel grid without allowing different parts of it to move out of sequence. If one side rises too quickly, forces redistribute through the structure. Geometry changes, connections move away from their intended positions. So synchronization becomes critical. The roof was assembled at a lower working elevation where construction and inspection were easier. Then 74 hydraulic lifting units were distributed around the structure. Instead of a few cranes carrying the entire roof, many controlled lifting points shared the load. Sensors and computer control monitored the movement. Then the roof began to rise. Slowly. For an operation like this, speed is not the objective. Control is. Thousands of tons of steel moved upward as one connected body. The lifting points had to remain closely synchronized while the roof traveled about 23.7 meters, roughly 78 feet, toward its final elevation. As it moved, engineers monitored alignment and the behavior of the structure. Eventually, the roof reached the level of its permanent supports. Connections could be completed. The temporary lifting system could give way to the permanent building. A roof assembled lower down now stretched high over the future station. It was one of the project's most dramatic construction operations. And for a moment, it looks like the roof problem is solved. But elsewhere in the complex, engineers faced almost the opposite challenge. First, Chongqing East had a roof that rose. Then, it had a roof that slid. The roof over part of the integrated transport center extended across an area roughly 236 meters long and 116 meters wide. At its highest point, it sat about 57 meters above the floor below, around 187 feet. The height was only part of the difficulty. The structure underneath was already complicated. Different levels intersected. Columns, transport spaces, and building zones made conventional roof erection directly above the final location difficult. So engineers changed the construction sequence. Instead of assembling every roof section where it would permanently remain, parts of the roof were assembled in locations with better construction access. The sliding zone was divided into 5 major units. Those units were assembled on elevated construction platforms. Then the roof itself was moved toward its final position. Think about what that means. Normally, a building remains stationary while cranes bring pieces to it. Here, building scale sections were assembled first. Then the structure moved. Together, the 5 sliding units weighed roughly 1,800 metric tons. A synchronized system using 19 pushers controlled the motion. The units advanced gradually along their sliding paths. Again, precision mattered more than speed. A structure hundreds of meters across cannot arrive merely close to the right position. Supports, connections, and surrounding steelwork have to line up. The final movement was controlled at millimeter scale. From the ground, the motion would have appeared almost impossibly slow. But that slow movement was the engineering. A building-sized roof was being pushed horizontally high above the floor while the complex below remained in place. One roof rose vertically, another moved horizontally, and underneath both of them stood some of the most visually unusual structures in the entire station. The tree-shaped columns. There are 40 of these tree-formed columns across the project. The largest rise about 41 meters, roughly 135 feet. At the top, the crown of the largest examples spreads around 29.6 meters across. Place a person beside one, and the scale becomes clear immediately. These are building-scale tree-shaped steel columns that combine structural function with the station's architectural identity. Their form draws on the huangjue tree, a familiar symbol of Chongqing. But creating that form at this size is far more complicated than making a conventional rectangular column. The geometry curves. Branches spread outward. The exterior surfaces change shape continuously. That requires individually fabricated pieces to fit a complex three-dimensional form. Digital construction tools became essential. BIM models helped coordinate the geometry. Three-dimensional scanning allowed construction teams to compare the installed structure with the digital model. For some of the giant columns, installation accuracy was controlled to around 2 millimeters. That contrast says a lot about modern megaproject construction, a structure more than 40 meters tall, yet parts of its geometry controlled at the scale of millimeters. By this point, Chongqing East already looked like a finished architectural landmark, but a spectacular building is still not a functioning railway. The structure needed tracks, railway power, and signaling systems, platforms, passenger systems, and all of the equipment required to move trains safely through the hub. The railway yard was designed around 15 platforms and 29 arrival and departure tracks. 15 platforms, 29 tracks. That order matters. The completed structure still had to be transformed from a construction site into an operating transportation system. Track work had to connect the station with railway approaches. Power and signaling had to support train operation. Platforms needed lighting, passenger information, safety systems, and vertical circulation. And all of that had to work inside the structural organization created years earlier. This is where the bridge building idea becomes easiest to understand. A high-speed train arrives on one level. Passengers step onto the platform. But beneath that railway, useful hub space continues. People move vertically as well as horizontally. Escalators, stairs, and elevators distribute passengers through the enormous building. Road traffic approaches at different elevations. Urban rail connections meet the hub below. And the station uses four-sided entry instead of relying on one conventional front entrance. That matters because a building this large cannot funnel everyone through one side. Passengers arrive from different parts of the city. Vehicles approach from different roads and different levels. Public transportation connects through different layers. The station has to accept all of those flows, reorganize them, and then move people toward the correct train. At this point, the final engineering challenge is no longer the roof. It is movement. The integrated hub was designed to connect national railway services with urban rail and road transportation. Multiple metro lines were planned around the wider Chongqing East complex. But not every planned line was operating when the railway station opened. The Line 6 East Station section entered initial operation together with Chongqing East in June 2025. Other planned urban rail connections belong to the wider network development around the hub. The purpose of the vertical layout is to reduce the distance between these transportation systems. A passenger arriving by high-speed rail should not have to leave the entire complex, cross a large outdoor district, and then search for another mode of transportation. Instead, much of that transfer can happen inside the same integrated hub. Official operating material has described some transfers between rail systems as possible in roughly 5 minutes. That does not mean every passenger can reach every point in the building in 5 minutes. It shows what the design is trying to achieve: shorter transfers, clear vertical separation, and multiple transportation systems connected through one building. Follow a passenger through the finished station. A high-speed train enters beneath the huge roof. The passenger steps onto a platform. Vertical circulation carries them away from the railway level. They can move toward road connections and station exits, or continue through the hub toward urban rail. Another passenger may arrive from the city at a different elevation and move upward toward the railway. Cars, buses, taxis, metro passengers, and high-speed rail passengers all use different parts of the same structure. That is why the station's size is only part of the story. The real challenge is making every layer work at the same time. On June 27, 2025, Chongqing East Railway Station officially entered operation. After just over 3 years of major construction, high-speed trains began moving through a structure that had once existed only as stacked layers on engineering drawings. Passengers could circulate through space created underneath railway infrastructure. Above them stood roof sections that had been lifted or slid into position. Around them rose enormous tree-shaped columns. And outside, bridges, tunnels, and roads connected the station back into one of China's most complex mountain cities. From the air, Chongqing East can look like one enormous building. But almost every major engineering decision inside it traces back to the same constraint: the terrain. The changes in elevation pushed the hub vertically. That made it possible to create useful space beneath the railway, but it also created enormous structural challenges above it. One roof had to rise, another had to slide, and the finished station now connects trains, roads, and urban transit through the same layered piece of city. Chongqing East was not built by making a mountain city behave exactly like flat ground. The terrain was not simply a problem engineers had to remove. It became one of the reasons the station took the form it did.